goal today is to write or create a function that performs the Gauss-Seidel method for linear systems, and specifically we'll be looking at matrices A that are square. Okay. And so we have a system here of 3 equations, 3 unknowns. Okay. And when we performed the Gauss-Seidel method yesterday, the first step was really to solve the first equation for x1. So that looks like x1 is equal to, and actually, yeah, I'll leave it like this. x1 is equal to, and then we're going to need to move everything over, so we're going to have minus a12 x2. And also keep in mind, we will have to divide both sides of the equation by a11 as well, so I'm just going to do that right now. Divided by a11, and again this was x2, and then we'll have minus a13 divided by a11, and then we still have the plus b1, okay, but remember we had divided both sides of the equation by a11. So there's our first equation, and then our second equation. If we solve it for x2, and we divide both sides of the equation by a22, then is what we'll have is we'll have minus a21 divided by a22 x1 minus a23 divided by a22 x3, and then plus b2 over a22. And then one more, we want to solve for x3. Okay, so if we solve for x3 here, that's going to give us minus a31 divided by a33 x1, and minus a32 divided by a33 x2, and then finally plus b3 divided by a33. Alright, and so now that we have x1, x2, and x3 solved for, let's try and remember what we did with these equations yesterday. Well, what we did is, since the first equation, okay, and actually I'm seeing a missing variable here. I should have an x3 right here. There we go. So what we do is we would pick a value for x2 and x3, and we'd substitute that into the first equation, and that would give us an estimate at x1. Okay. And then we have an estimate for x1 and x3, and so we'd make a new estimate for x2. Okay. And again, we have a new estimate for x1 and x2, and so we'd use that to find a new estimate of x3. Okay. And then we'd just repeat the process over. We'd come back to x1 using our updated x2 and x3 and approximate it. We just keep doing this over and over and over again, and in some situations it converges. Okay, it converges on the answer. One way, remember, that we can tell whether a system will converge or not is if it is diagonally dominant. So meaning that if we look at one of the rows, if the element that's on the diagonal is bigger than all the other elements in its row, okay, that's a good thing. And if this is true for every row, then it would be diagonally dominant. We know it would converge. But do note, it still can converge even if it's not diagonally dominant. Now, the next question is what are we going to do in Matlab as far as this goes? Well, for one, it's not going to be quite as simple as this because we don't know. We want this to be able to work with a system of any size. We don't want to only make it work for a 3 by 3 like kind of what we're describing here. And so in order to make sure that we can make this work for any size, we're going to need to think about this problem a little bit differently. Maybe actually using matrices. So let me put a little note here. It's actually from our book. Notice that the solution, that's the part in green, can be expressed concisely in matrix form. Okay. And let's see what that is. X is equal to D minus the matrix C times X. So that part in green there can be represented like this, but the question is, what is D, what is C, and let's see what those are. Where D is equal to, so this is going to be your B vector after you've divided by A11, A22, A33. So this is B1 over A11, B2 over A22, and B3 over A33. So when we actually go to write our code, this will be something that we have to create, is this vector D. And we'll also need to create another vector. And actually, I should say matrix C. And let's see here. So the matrix C is going to have everything in this system up here other than these B's. Okay? And we'll see why that's the case here in a minute. So if you look at this system of equation and you ignore the B1 over A11, B2 over A22, and just look at the parts that contain X1, X2, X3. Okay? Notice that in the first equation, there is no X1. In the second equation, and I'm talking about the right-hand sides here. I should be a little more clear. In the first equation, there is no X1. In the second one, there is no X2 on the right. And in the last one, there's no X3 on the right. So what that means is we're going to have some matrix, and it's going to have zeros along the diagonal. Okay. And then next, we're going to fill in all of these coefficients for, say, X2 and X3. So minus A12 over A11 will be the first thing. Okay. And actually, I should even say another thing. Since there's already a minus sign here, I'm not going to need to say the minus. I'm just going to be able to do A12 over A11. So A12 over A11. Scooting this over a little bit. And then the next one was A13 divided by A11. And the one that would have to go here would be A23, because we're in row 2, column 3, divided by A22. And then over here would be A21 divided by A22. And then down here we'll have A31 divided by A33 and A32 divided by A33. And so one thing I'd like us to actually see is that this indeed really is the same thing as what we had up there in the green. So let's maybe just make a little bit of side work here. So if we were to actually go and compute X equals, and actually, yeah, X equals D, so that'd be this B1 over A11, B2 over A22, and B3 over A33, and we were to subtract this other matrix, which maybe I'll just copy and paste it. That might make it easier. There we go. And right, we still wanted to do this times x. Still wanted to do this times x. So then up here we should have x1, x2, x3. Okay. All right, well, let's do some multiplication. Okay. I want to do this operation here first. I want to multiply this matrix by this vector. Okay. So we'll still have our B1 divided by A11, our B2 divided by A22, and our B3 divided by A33. That one's easy to write. And minus over here, let's see what we get. So we'd get 0 times x1, and then A12 divided by A11 times x2, and then after that we'd get plus, and it would be A13 divided by A11 times x3. Okay. And actually, maybe we'll just do the top row, because I think you might be starting to see this. And if I were to simplify doing this vector minus this vector now, we'd have that B1 divided by A11 minus both of these terms. So I'll zoom out a little bit, or move this over a little bit. Minus A12 divided by A11 x2, and minus A13 divided by A11 x3. Let's see if this matches the first line of what we have in green. Okay. And remember, over here where we have x, this top line would be x1. So x1 equals, okay. And notice again, we do have that B1 over A11. If we go down and look here. There we go. It's just we have it written at the end rather than at the start, which isn't a big deal. Okay. And then notice the other two terms seem to match up here too. A minus A12 over A11 x2, and minus A13 over A11 x3. Okay. And if you finish doing the multiplication here, filling this all in, subtracting, you'll see that we get these same two bottom equations here. Okay. Now I'm going to get rid of some of this clutter here of our side work, but what we're going to do next is we're going to go into Matlab, and we are going to create this function. All right, we are in Matlab, and you can see we have our function. It has an output of x, has inputs a, b, es, maxit. The function name is Gauss Seidel. Okay, and let's talk about what those inputs are. So in our system of equations, if you're looking at ax equals b, then a would be the matrix, b would be the other side of the equation, es is our relative error, right? And maxit is the maximum number of iterations. Okay. All right, so let's see here. Let's start off with the Nargan stuff. So if Nargan is less than 2, we would like to say that there is an error, okay? And that error is, we need at least 2 inputs. We need the other side of the equation, right? ax equals b. Okay. Without that b, there's nothing, we don't have a complete equation. Okay. So error, at least 2 input arguments required. And if nargan is less than if nargan is less than 3, let's set some, or actually, if nargan is less than 3, or is empty for ES, okay, then is what we'd want to do is we'd want to set the default for ES to be 0.00001, okay, and end that one, and then if nargan is less than 4, or if maxit is empty, then we'd want to set that default at 50, okay, and end that. And next, we want to take a look at the size of the matrix A. And the reason we want to do that is if this thing's not square, we would need to do a different technique, or we'd need to adjust our code, would maybe be another way to word this. Okay. So if m tilde equals n, so right, that means if m is not equal to m, we want to display an error. Matrix A must be square. All right, and then the next thing that we want to do is we had noted that we wanted to create some matrix C. And in order to do that, let's just start off by actually saying C equals A, because C and A actually have quite a bit in common. Okay. C looks a lot like A. It's just that we've divided all of the elements by or we've divided each row by the diagonal elements. And we also have a bunch of zeros along the diagonal of C. Okay. But it looks somewhat similar. Okay. So this isn't a bad starting point. Let's go ahead and fill in those zeros. So for I equals 1 to n, and so then we have C of I comma I, right, the diagonals, is equal to 0. Okay. And you might be wondering what I'm about to do here, x of I equals 0. Okay. Why would we want to fill x with a bunch of zeros? Okay. Well, this is going to be our initial guess. Okay, we're just going to say we think x1, x2, x3, however many x's we have, we're saying that we're going to start off with 0. Okay. All right, so next thing we're going to do is we're going to turn x into a column vector. Okay, we're going to want it to be a column vector because we're going to actually do a matrix times a vector, and we need those dimensions to match up correctly. Okay. So we've turned it into a column vector. Okay. So next we have 4 I equals 1 to n. And actually, I want us to go back to our OneNote for just a second to see what we had there. Okay. So if you do look at the matrix C, right, A12 is still in the right spot. It's just been divided by A11. A13 is still in the right spot. It's just been divided by A11. And I could say that about the rest of the non-zero elements. They are just A divided by their corresponding diagonal. All right, well, let's go back into Matlab and make that happen. So we are going to say C of, not 0, I, comma, 1 to n is equal to C. So is what we've done here is we've taken, say, row I, and we are going to also keep in mind when I say Ci, comma 1 to n, that C right now is filled with the elements of A other than along the diagonals, because we made the diagonals 0. So this is taking the matrix A, and now we are going to divide by the corresponding diagonal. All right, this is taking row I and dividing by the corresponding diagonal. All right, we'll end that one. And let's also create a vector D. So for I equals 1 to n. And we have D of I. And this one's a little bit easier. You might remember this one was just the B vector. Okay, the B vector divided by the corresponding diagonals. So B1 was divided by A11, B2 was divided by A22, and so on. So the ith element of D should come from taking the ith element of B and dividing that by the corresponding diagonal of A. We can end that. So we've created C, we've created D, and finally, now that we've created those matrices and vectors, we can start our while loop. Okay. So before my while loop, I'm going to have iter equals 0, because we need to count the number of iterations, because we have max it here. All right. Then while 1. Okay. And we are going to be computing a relative error, so I'm going to want an x old in here. Okay, so x old is just equal to x. So every time this while loop runs, x old becomes the previous x. Okay. That makes sense. And then we need to start a for loop so that we can compute each one of the rows. And so it might be helpful for us to switch over to OneNote so we can kind of see how that's going to work. Let's just maybe think about row 1 here. Okay. So if we're thinking about row 1, meaning we want to calculate x1, the question is, well, how could we do that? Well, we could take the first value of D, subtract, and we'll actually take the first column of C, and we'll dot this with D here. Okay. So dot this with X. Remember, we turned X into a column vector. Okay. And we did this that way the dimensions matched up, because this one here is a 1 by 3, while this is a 3 by 1, and we need those inner dimensions to match, and they do. And so let's see what this does. Okay. If we were to compute this, we'd have B1 over A11 minus, and remember, when you multiply these two things, this is equivalent to the dot product. Okay. You can also think about it as matrix multiplication with a 1 by 3 by a 3 by 1. But this is really just the dot product. So this is going to wind up looking like A12 divided by A11, x1, and plus A13 divided by A11. And, oh, I made a little typo, right? It was 0 times x1 gave us nothing. And then we should have this times x2. So this should just be an x2. And this one over here should be times an x3. Okay. Just doing the dot product. Okay, and notice again, this matches, if I move this up, it'll match our green equation that we have up there. Let me go ahead and move that up. Right, you can see the B11, or B1 over A11, the minus A12 over A11 X2, and plus, well, actually it'll be minus, right, if I distribute that negative, minus the A13 over A11 X3. All right, but if we were to think about this in general, what did this look like? Well, this looked like x of I is equal to d of I, right? Because this is came from d of 1. And then minus, okay, and remember this came from the first row of C. So if we were to do that, we'd want to say row I, and then everything, okay, every column of that row. Okay. And then this was times x, okay, the whole vector x. All right, well, let's go ahead and code that in. All right, so there we are. We have our, again, x equals x old, and we're going to start that for loop that we were just talking about. So for I equals 1 to n, okay, we're going to have x of I is equal to d of I minus c of row I, and then times the vector x. Okay. And the next thing we'll want to do after that is we are going to want to compute the relative error for this specific x, right? We're going to do it for x of 1, x of 2, x of 3, as long as that individual x is not 0. So if x of I is not equal to 0, so I need my tilde, so if it's not equal to 0, okay, then our relative error, we're going to need a relative error for each one of those x's. So our relative error is actually going to be a vector. Okay. So it should be the absolute value. Okay. And I want to do x of I minus x old of I. Okay. And then we'd like to divide that by x of I. And I just want to double check my parentheses here. Maybe I'll space this out a little bit. Okay. All right, and that is looking good. And the only other thing I want to do here is multiply this by 100 to turn this into a percentage. We will end that. And finally, we're still in the while loop, right? So we would like to count our number of iterations. So iter equals iter plus 1. And then finally, we need the stuff that might break this while loop. So if the max, so we want every single one of the x sub i's to be within the desired accuracy. So we want the biggest one of them, the biggest error, to be less than or equal to ES. Okay. Or we'll also potentially break our while loop if the number of iterations exceeds or becomes equal to max it. So break and end. Okay. And then finally, we can write our end for the while loop. Okay. And that's it. All right, we are actually missing one end here. And after we replace that end, we're going to go test this function out on an example from yesterday. But the end we're missing is we ended this if statement here but we never ended the for loop that we had there, so we need that. There we go. But yeah, let's go to this example from yesterday, but we'll use our function that we've just created. But let's not forget to hit save there. Okay. All right, so here it is. This was the matrix A, the vector B for AX equals B, and we'll just use the defaults for ES and max it. Okay. Let's go ahead and hit run. Okay. And this seems to be matching what we had yesterday when we used the backslash command. Let me go ahead and hit run here too. Okay. And yeah, both of these are producing the same answer. So looks good.